So, let me first thank for the introduction and thank the organizers for the invitation to come here. I think this is the second trimester program on non-commutative geometry, and I hope that a kind of tradition has been started, but well, that's what the organizers maybe have to think about. Anyway, so I'm glad to be here, and today I want to talk about joint work with Hessel, Posthuma and Tang on the transverse index theorem for proper cocompact actions of Lie groupoid. So essentially this is on index theorem over Lie groupoids. The index theory over singular spaces has a long tradition and is still active research, and we would like to have a contribution to that area by these papers. So my talk is essentially based on this second paper here, which will appear in the Journal of Differential Geometry, and also very much related to this paper on the localized longitudinal index theorem and the index of geometric operators on Lie groupoids, which will appear in Indagationes. Okay, so these are the my collaborators. Hessel is here, Tang cannot come, but he has a good excuse. He just sent us a message yesterday that he became father for the second time. So anyway, let me just start with a brief tour through index theory as a motivation. And I recall here the famous Atiyah-Singer index theorem, also to, just to introduce some notation. So if D is an elliptic operator on a closed-oriented n-dimensional manifold, you all know that it's Fredholm and that its analytic index can be given by the formula on the blackboard. And what I will need for the following are the following observations. The symbol is an element in K0 of T star of M, and in this formula CH is the Chern character, and a roof is the a roof genus of the cotangent bundle. Another part or a theorem which led to modern index theory is the Lefschetz index theorem. I just cite that here for reference and completeness, but more important for our work is the L-squared index theorem by Atiyah. And here you start with a unimodular Lie group which acts on a smooth manifold M, and you assume that D is a G-invariant elliptic operator. And then you have the observation that the kernel and the co-kernel, they are equipped with G representations. So what the consequence of that observation is that you can regard this formal difference here as an element in K0 of the reduced C star algebra of G. And then you can define the L-squared index of D as the following. You apply the trace onto that index class here. And then there's the following result by Atiyah. So if you have a closed manifold and D, again an elliptic differential operator, and you look at M, which is supposed to be the universal covering of X, and G will now be the fundamental group of X, what you can do then is you can lift this operator dx to a G invariant elliptic operator dm on the universal covering, and the L squared index of that dm is equal to the analytic index of dx. So these two are related by this theorem of Atiyah. And so one of our intentions was to, in a certain sense, have a generalization or of that to Lie groupoids. Okay, other important theorems from index theory are the family index theorem by Atiyah-Singer, the higher index theorem by Cohn-Moscovici. I will explain a little bit on this in the following, because as the title of the talk already it's not in the title. It's the index theorem I will introduce or explain is also a localized index theorem. And this localization technique essentially goes back to the work of Cohn-Moscovici on the higher index theorem. And then also an important theorem in this whole index theory business is the foliation index theorem by Kohn-Skandalis, which can also be reinterpreted as a certain special case of a groupoid index theorem. Okay, and finally, the L-squared index theorem for homogeneous spaces, again by Kohn and Moscovici. Okay, now let me just come to one conjecture by Kohn and say a couple of words on this. So you look at a properly groupoid. G is the error space, M is the object space. Details of the definition, the precise definition I think was in the talk before lunch. And you assume that D is an elliptic G differential operator along the fibers of the source map. Then Kohn has defined an analytic index class in the K-theory of the convolution algebra of G. And using that framework, essentially all the previous index theorems which I had on the slides, they can be recast in exactly that framework of Lie groupoids as set up by Kohn. Now, Kohn has made one suggestion in one of his papers, namely to give a topological expression for that index class in the K-theory of the C-star algebra. So equating this with a topological index, and that hasn't been fully achieved yet. What one can do is, pair this index class with other classes and then write down a topological expression for that pairing. Yeah, but that Kohn suggestion is even more, and we hope that our work is a little step into the right direction. Anyway, so let me now go more into details. As in the talk before lunch has been pointed out, there is an index map, and it goes from the K1 of the continuous function on the cosphere bundle to K0 of the compact operators on M, which is equal to Z. And in the following, I need a more or less precise construction of that index map. So I just write it down in some more precise terms, because it will come later again. So we start with A, which is an elliptic symbol. So it should be an elliptic symbol. You can, for simplicity, assume it has order 0, but that's not really necessary. And that what you do next is choose absidio A, capital A, such that the symbol of this operator is this little a. And you also choose B a parametrix, so it is again a pseudo-differential operator. So in particular, sigma of B should be the inverse. And you can do that in such a way that 1 minus AB and 1 minus BA, that these are all pseudos which are smoothing. And you give those two guys a name. That's S0 and that's S1. Okay, and then you have an auxiliary construction, which is L. It goes S0A, S1 minus B minus S0B. And you observe that that is invertible. And you now define the index class of that symbol to be the class of R, where R, the K-theory class of R, where R is P minus E, and P are two projections. P is equal to L I 0, 0, 0, L inverse, and E is equal to this projection. So you just go higher in dimension. The main observation, and that's why it's called the index, well, it's an easy exercise to just check the trace of R equals the analytic index of the of capital A. Yeah. So. Okay. I wrote that down in a little bit more detail because this R will be needed later to understand properly Kahn-Moskowitzy's approach to localized indices. Okay. Kahn and Moskowitzy in the paper which I cited above on cyclic cohomology and the Novikov conjecture and hyperbolic groups, they draw the following observation, that the analytic index does not capture fully the local information which is carried by the symbol. And they kind of remedied that defect is maybe the wrong word, but they introduced a localized index which contains even a local information about the symbol. And how was that done? They use Alexander Spanier cohomology to achieve that. And let me just briefly remind you of what that is. You look at a topological space, or in our case it's a manifold, and you look at ck of x. What is that? That's a space of all smooth functions f from the k plus 1 power of x to r. And you have phase maps, delta I, so they are just, you leave out the ith coordinate. And it's easy to check that these phase maps fulfill the commutation relation of a cosimplicial space, and to be precise, a semi-cosimplicial space. And then you get, well, you can define a differential, but the corresponding cochain complex is acyclic. What you can do is you look at the subcomplex of those cochains which vanish in an open neighborhood U of the diagonal, so to speak. Yeah? So you take an open covering script U of x, and you look at all those f's which vanish on this U to the power k, where you take the k plus 1 powers of this neighborhood U. And then you look at the quotient complex, and that complex is not acyclic anymore, but that complex is the Alexander-Spanier complex, and its cohomology is the Alexander-Spanier cohomology of X. So there are a couple of fundamental observations with this. For reasonable topological spaces, it coincides with singular cohomology or check cohomology, but what is important for manifolds, there are maps, quasi-isomorphisms between the Alexander-Spanier complex and the de Rham complex on M. And so that was, by the way, this is already a localization here, this passing to those chains which vanish around the k-diagonal. Okay, now I come to the localized k-theory. So Kahn-Moskowitzy did not introduce that. That was work later by Moskowitzy and Wu. And how is that done? So you look at the smoothing operators on M, and again you have script U is a finite covering, and you define this algebra of pseudos on M which are supported in U2, where the U2 is defined by this formula here. Okay? So it's also supported in a small neighborhood, so to speak, of the diagonal. And when you let U becomes a finer covering, then the support is concentrated closer to the diagonal. Okay, and then you look at M infinity, n cos the infinite matrices, so to speak, with entries in these pseudos, and define K0 as the following space. So these are pairs P and E, both are projectors, what you can see here, and the first one lives in the unitalization of that space, and the second one is just an infinite matrix in C, such that the difference lies in is a matrix in psi minus infinity mu, and you mod out by an equivalence relation. Essentially, it's a homotopy relation between two pairs. Okay, now you get a bunch of those, namely for each finite covering, and if you have a refinement, then you get a map from the finer to the coarser. And what you can do now is you can form the inverse limit or the projective limit of that projective system. That obviously does not depend anymore on coverings, and that is our new K-theory, namely the localized K-theory on M. Okay, so now we want to apply that to an index problem, and we have given an elliptic operator, and one wants to define a localized index which sits in there, and that is essentially, how is that done? That is done using that R, and maybe I'll write that down. Let me just write that. I'll write that down later in the pairing. But anyway, so one has a localized index now in here, which comes from these R's. What you can achieve with these R's, in principle, for each of these finite coverings of M, you can find an R by proper choice of the A's and B's, such that the support of that R is exactly in that U squared. Yeah. So if you make that smaller, you get a family of RUs. And obviously that then defines a localized K-theory class in here. And that is exactly the localized index class of the operator D. I should have, well, the D here coincides with the A there, so maybe that wasn't, maybe I write here is equal to D. Yeah? So that's how that index class is constructed. Okay, so and that's the map you then obtain by the construction I just verbally explained. Okay, finally there is a kind of a forgetful map which forgets about the localization, and if you compose that with that, then you get your original index map. Okay, now what one wants to do is extend these ideas to proper cocompact G manifolds, where G in this case is a Lie group, or even more generally of a left action of a groupoid G on a manifold Z. And in both cases, one can define localized K-theory groups, K log of the invariant pseudo-differential operators on M, and here also of the invariant smoothing pseudo-differential operators on Z along the foliation. F is the foliation which is defined by the left action of G on the manifold Z. I will explain that in a little bit more detail later, but already at this point I can refer to the previous talk because there these operators were defined in detail by Denis. The construction of these localized K-theory classes is kind of similar. You have to be a little bit more careful because about what neighborhoods you choose, because you do not have really diagonals anymore. But what you can do is you can look here at neighborhoods of the unit space in the groupoid, and you can kind of narrow these neighborhoods down to the unit space M, and you get likewise a projective system of K-theory groups of operators living in this psi minus infinity and supported in this neighborhood of the unit space, and that projective limit is exactly this one, respectively this one. So it's more or less a technical construction, but it works the same. Now, I have defined Alexander-Spanier cohomology, but we need to relate it to, which is also localized theory related to localized K-theory. So you assume that phi is an Alexander-Spanier cohomology class. So it is a function on mk plus 1, and you assume that D is an elliptic differential operator. Now here these R's are exactly these R's, and as pointed out, you can make them localized within a neighborhood U of the diagonal, or U squared, because we are working on M cross M. Now, Kohn-Moskowitz defined the index of D localized at that Alexander-Spanier cohomology class by the following formula. Yeah? You integrate over the k plus 1 product of M and take the trace of these because R is psi minus infinity. That is well defined. And one has to show that everything is independent of choices, but that is the case. And okay, now what did Moskowitz-Wu do in their paper? They kind of reinterpreted this formula as a pairing within Alexander-Spanier cohomology. So they took the localized index class, as I just defined it within the localized K-theory, and constructed an AS, Alexander-Spanier Chern character, that's maybe the proper name, from this localized K-theory class into Alexander-Spanier homology. And then you take just the natural pairing between Alexander-Spanier homology and cohomology, and that coincides with the localized index. I will not go further into detail with this, but that's a certain motivating idea for our work, where we also have localized pairings which we compare then to standard index pairings. Okay, so now let's come to the Lie groupoid case. So you know all the notation. I mean, M is the composition of errors, I is the inversion, S and T the source and target map, and U the inverse. Now, what is important is for the following is that we use a left action of G on a manifold Z, which is a submersion. Sometimes it's called a moment map, together with this action map, and that's not always defined. What you really need to observe is that the target of G coincides with mu of c, so that you kind of can really compose. And then, in case these products are defined, you have associativity, action of unit, and so on. Yeah, so these are the canonical axioms. So, given such a groupoid, as I already have mentioned, one obtains a natural foliation of that manifold Z on which the groupoid G acts. And this defines an involutive subvector bundle T mu Z, and that bundle carries a natural G action. Yeah? So what does T mu Z consist of? It consists of all vectors, or all tangent vectors, which by the tangent map of mu are mapped to 0. Yeah? So because this is an involutive subvector bundle, it defines a foliation, and that's exactly the foliation F. Yeah. So, yeah.
Why is the foliation? Don't you get drops in dimension?
No, because as I mentioned here, this is a submersion. Yeah, that's.
So it's not a general.
No, it's not. It's here. I mean, maybe I should have mentioned this more loudly, but it's a submersion, and that guarantees that you do not have drops or changes in dimension. Yes, that's okay. Now, just as an example, so you look at G acting properly and co-compactly on a manifold C, and then you can look at the action groupoid and the groupoid over a point. They both act on C. Okay, now we come to the generalization of pseudo-differential operators to this situation. Now, what is an elliptic G-invariant pseudo-differential operator on C? That is a leafwise elliptic pseudo-differential operator, D, meaning it acts really on the leaves, and which is invariant under the G action. This invariance under the G action is possible because G acts on that T mu Z. Yeah. By the way, an important observation and remark at this point is G in general does not act on the tangent bundle of the object space, which causes, in several instances, somewhat of a trouble. But anyway, so the principal symbol then is a function on the cotangent, on the dual bundle of T mu C, and essentially that's a leafwise symbol of D. And obviously this symbol is G invariant because D itself is by assumption G invariant. So, and the notation I already have mentioned this, I think. So, that's the notation. Okay. Now we have the algebra of operators I'm talking about, but we need now replacements of the Alexander-Spanier cohomology. And to this end, I introduce first, I mean, this is well-known stuff, but the localization is then the new material. So if you have a Lie groupoid G, you get a simplicial manifold in the following way. You look at the composable arrows. Gk consists of k tuples of G, of arrows, such that they are composable, so the source of one coincides with the target of the next one. By the way, this easily shows that the arrows go in this direction. Yeah, I mean, that's always a choice, but just to avoid confusions, that condition means the arrows go this way. Yeah? Okay, and that's also the reason why here I had here T of G needs to coincide with mu of C, yeah? Because arrows go in this way. Okay, Now this is a simplicial manifold, so you need phase maps, and the phase maps, I did not write them down explicitly, but these are essentially this one, and this one. And you add them up in an alternating fashion, and then you get the differential on those CKGC, on those K differentiable cochains over the Lie groupoid. Okay, and it gives rise to cohomology, and that's the differentiable groupoid cohomology. Yeah. So that's diff G. Okay, now, it's already here. Now, what you can do is, and that's the localization. You can look at the space of infinity jets at M. M is, again, the object space. So it sits naturally in the GK, I mean, kind of by diagonalization. And instead of looking at all smooth function on GK, you look at germs of those functions at that M, at that unit space. And it's clear that the differentials I had here leave the germs invariant. Yeah? Therefore, no, was that the wrong direction? Yeah, here. So the differential leaves the germs invariant, so you get a new complex. And in fact, you get it even with a natural map from this space to these spaces here. So, and because commutativity with the differential, you get even a cochain map, to be precise. Yeah. So the D naturally induces a differential on this, and the cohomology you get out of that is the localized groupoid cohomology, or the localized groupoid cohomology. And now, when you look at the pair groupoid M cross M to M, now you can ask the natural question: what is the localized groupoid cohomology for the pair groupoid? That's exactly the Alexander-Spanier complex. That's an.
Germs, not jets, as you've written.
Pardon?
So you're taking only germs, not jets, as you've written on the slide.
What?
Something about jets.
Oh yeah, okay. That's right. That's right. The point is that, I'm jumping back and forth between germs and jets. The point is, from the germs you can pass over to the jets, and that's a quasi-isomorphism. Yeah. So if you prefer Whitney functions, jets, you work with that. If you prefer germs, you work with that. You're right. I talked about germs and have written jets, but this is these two complexes are quasi-isomorphic. You can work with either one of them. They are cohomologically the same. Does that answer the question? Okay. So now what is an important observation is that this localized groupoid cohomology can be naturally identified with the Lie algebraic cohomology of A of G. Maybe just to remind you, A, the Lie algebraic of G is defined as the kernel of dt restricted to the unit space. Yeah? So you take the tangent map of the target map and take the kernel of this and restrict it to M, and then you get a bundle A over M, and that's the Lie algebraic. Okay, and Lie algebraics carry a natural cohomology theory, which is kind of modeled from standard Lie algebra cohomology, and I've written down here the corresponding differential, the Lie algebraic cohomology differential, and that's one of our theorems, is that the localized groupoid cohomology is naturally isomorphic to the Lie algebraic cohomology of the Lie algebraic associated to G. Okay, now we kind of have the replacement of the Alexander-Spanier cohomology in the groupoid setting, and that's the localized K theory. The localized differential, the localized groupoid cohomology. But what we need is the localized K theory, and there I don't need to go into details how to define that, because that's kind of not word by word, but very similar to the construction I showed here on the slides, a la Moscovici-Wu. Again, you do not localize around diagonals, but around unit spaces. And you get, again, an inverse system of K groups, and that limit is then the localized K theory of this algebra of pseudo-differential operators along the foliation. Likewise, if you have D, an elliptic G invariant differential operator, you define its localized groupoid index in here exactly in the same fashion. Yeah? For this, because it's elliptic, you can fiber-wise find those R's. You can, again, shrink the support in the fashion you want to. Hence, this family of RUs defines exactly a localized K-class in here. So that's the same idea. Now what needs to be done is you need a pairing, and that's here. Now here things that's a little I haven't explained that really yet, but I come to this. This is a space which is isomorphic to the localized groupoid cohomology. What is it? This is the cohomology of the following complex. So you look at H dot F Z U star L is cohomology of the space omega dot F. So what are these? These are forms on the, leaf-wise forms on the foliation. And, well, it has a natural differential, and its cohomology, that's exactly this one. Here I have it within certain values, and I have to explain what that is. Mu was the moment map, which you remember went from Z to M, and L, that was, L is a section guaranteed by unimodularity, guaranteed, which silently has been assumed here, unimodularity of the groupoid G, and it's a section of L top and nowhere vanishing section of L top T star M tensor lambda top A star. So the dual of the Lie algebroid. And on G acts on that bundle. I mean, as I pointed out before, G doesn't always act on bundles or on T star M or Tm, but on this bundle it acts naturally. And this L can be regarded as a groupoid volume form. Yeah, and unimodularity guarantees the existence of this. And then you look at that cohomology theory. And this now naturally pairs with that one. Okay. And the observation is also that H dot F Z U star L G is canonically or is naturally isomorphic to the localized K theory, GZ. Okay. Now I come to the Van Est map. Well, its construction is somewhat technical, but maybe first a couple of remarks on the Van Est map itself. The classical Van Est map essentially is a map from differential group cohomology to the algebraic cohomology and relates those, and in the same fashion that can be extended to differentiable groupoid cohomology. And Kreinig, he constructed a generalized Van Est map or a groupoid Van Est map, and this is the map we have here used here as well, even though in our paper we used a somewhat different construction or another way. But what's in the center of the construction here is kind of, as I pointed out to you, there is a natural map that there's a natural map from the differential groupoid cohomology to the localized one, because the corresponding cochain complexes are related by a cochain map. Yeah? And defining this phi c, you use exactly that observation and have that in the middle, and in the right, on the right hand, on the left hand side, you compose with proper isomorphisms, and the composition of these gives you your phi c. That's the construction. Okay, and now the important theorem is the following. And what is the virtue of that theorem? It relates the localized index with the standard index in the groupoid case. So phi z of phi, so you apply the Van Est map where phi is a differential groupoid cohomology class. You apply it, phi z of phi, and then you pair that with the localized index class within a localized K theory, and then that is equal to the standard index pairing of phi with the index class of D in the K theory of psi minus infinity of Z. Yeah? So that's the important observation. Obviously, that can be transferred to the manifold case using the pair groupoid, and to all the other particular cases I mentioned before. Okay, so let me just look into. So now we have a final theorem, and which computes that localized index, and that is the following. It stands here. So again, you assume that G is a Lie groupoid which acts in a proper and cocompact fashion on a manifold C. D is elliptic. It is again invariant, and alpha, that's now an invariant theorem cohomology class along the foliation, and it's even. For the odd case, by the way, everything is 0, so we need only to consider even order cohomology classes. And then you evaluate this alpha with the localized index, and you get that formula here. So what you integrate over is over the dual bundle of the T mu C. I mean, again, the T mu C was the bundle along the leaves of the foliation. That's the A roof class of the dual of the foliation. That's the Chern character. So these are standard characteristic classes. What's a little or needs some explanation is this pairing of C with alpha. So what is C? little c, that is a cutoff function, c of x, which, well, it's non-negative, and it has, if you integrate it alone, it has some, gives you 1, and you pull back the pairing of this with pi star. Pi is the projection from t mu star c onto z, and so you can pull back that pairing, and this integral then coincides with the localized index. Okay, so that was essentially my talk. And what one can do is one can, in principle, apply that to some geometric operators on Lie groupoids. What one can also do is one can derive from this and the previous one all the previously mentioned index theorems, like the Skandali's foliation index theorem can be derived from this. Obviously, Atiyah-Singer, Kohn-Moscovich's higher index theorem as well, just by considering the pair groupoid. G is m cross m with a projection on m, both as targets and as the source and target maps. So you can recover quite a variety of index theorems from this one. Now, what is still a problem, and maybe just a little outlook, is, as you've seen, there is no cyclic cohomology or homology here in that picture. First, what one would have to do is, if you want to have a Chern character acting on localized K-theory, you would have to define a localized cyclic cohomology and homology theory as well. That hasn't been done. There are some ideas, but to define a proper localized Chern character, you would first have to look into localized cyclic homology theory. So that's, maybe I write that as an outlook. Define localized cyclic cohomology. And then construct corresponding Chern character or Chern-Kohn character. Yeah, that's one thing. The other point is the cyclic cohomology and even of these convolution algebras and HH of A, where A is the convolution algebra of a proper Lie groupoid, it's not known. Yeah? So not yet known. So in principle, to make progress in this whole program of understanding Kahn's conjecture or guideline, however you want to formulate it, you need to make progress in these two, for these two questions. Yeah? And there is there's quite something known in the particular case where G is a transformation groupoid, meaning where a compact Lie group acts on M. There the Hochschild homology has been computed by Bloch-Getzler and Brulinsky, but its generalization to the channel groupoid case or proper Lie groupoid case is still missing, even though there are some reasonable conjectures in this direction. Okay, I guess it's a good point to stop, and thank you for the attention.
How about computing this localized K-theory?
That's a good question. As far as I know, there is not much yet. I mean, there.
Isn't the Davenport case for the Con-Moscovici?
Well, Con-Moscovici did not use it. It was Moscovici-Wu who defined the localized K-theory. And they have one paper on this, and then I think there is another. I'm not sure whether it was Wu alone or with Henry, where I think they did something with Pontryagin classes and localized K-theory, but I'm not 100% certain. So I have to refer to their papers. It is just technically very involving. Yeah, so. And in particularly for that convolution algebra case, simply because you even don't know the cyclic homology, then the or not even, or even worse, you don't have a clue what the localized cyclic homology of that gadget would be. It becomes just a difficult question as well to compute the localized K-theory. Yeah.
So this may be a question in the same direction. Or if you just look at Czech cohomology, then you can, and if you take a good cover of your space for which the sets are contractible and all the intersections are contractible,
Yeah.
and you don't have to take this limit, is something similar true?
Oh, you mean no? I mean that is something what can be helpful if you look at the Alexander Spanier homology or homology, but not in the. The point is that K-theory is not a homology theory. Yeah, so it's that causes difficulties. Yeah, and the point is that's one thing. The other thing here is. Even if, I mean, the covering consists of contractible sets, the corresponding script U, the corresponding script U upper 2 consists of pairs U cross U, and you take all the union. So it's a neighborhood of the diagonal, which gets smaller and smaller. And if you look at this neighborhood, you lose these nice properties of contractibility. Yeah, so it's contractible to M, but M itself need not be contractible anymore. So these check stuff methods don't really work. At least would be my immediate guess, I would say.
Yeah, in the case of Con-Moscovici, the left-hand side is also the pairing between under favorable hypothesis on the group.
Yeah.
It's also the pairing between the Caesar algebraic index and a certain cocycle. Cyclic cocycle that you can define.
Yeah.
Do you have such a general statement?
No, not yet. So no, but that's again with, as you mentioned, with cyclic pairings with cyclic cocycles. Yeah. Even though in the original definition of that pairing, I mean they write index phi of D. It's a tau phi of, and then they insert all these r's. What they show is what you get out of this is a cyclic cochain, but you do not want to regard that one within cyclic homology because then you lose again the localization. You would like to regard that within a localized cyclic homology theory, which does not yet exist. I don't think it would be overly difficult to really construct it, but probably, I mean, along those lines I outlined, but nevertheless technical. I am not sure whether that would somehow go in the same direction you are asking, but could be.
Anything else? No, then thanks again.
Thank you.